Our next section will focus on how we name alkanes. Notice the ending of the word alkane is A-N-E, and we'll notice that each one of these hydrocarbons will have the same ending, showing that it is a saturated hydrocarbon. The IUPAC system is used most often to name these alkanes or any hydrocarbon found in organic chemistry, although there are some still remaining common names that this chapter will show us as well, but you can never go wrong in naming them according to the International Union of Pure and Applied Chemistry, which stands for the IUPAC. So it is the same system that we've used for inorganic nomenclature, applying it now to hydrocarbons. That IUPAC name for an alkane with an unbranched chain of carbon atoms consists of two parts. The first of the two parts shows a prefix showing the number of carbon atoms, and then the last part of it will be the suffix, which will always be ANE for this saturated hydrocarbon. In an earlier lesson, I suggested that you memorize those prefixes for the first 10 hydrocarbons. I hope you have started to do that. Methane, 1 carbon. Eth stands for ethane. Propane, butane, pentane, hexane, heptane, octane, nonane, decane, counting organic chemistry style 1 through 10. When we think about the straight chains, very simple, straightforward nomenclature. Say the name of the prefix, end it with ane, and you've named the first 10 of our hydrocarbons. If we have a branch coming off of a chain, it's known as an alkyl group, a substituent group derived from an alkane by removal of a hydrogen atom. We played around with those a little bit in the last section as we tried to draw constitutional isomers, creating branched chains. Keep in mind we work hard to find the longest chain, and everything else around that hanging off as little branches are known as the alkyl groups. We commonly represent alkyl groups as a general letter R. So however many hydrocarbons are hanging off of that branch, hanging off of the chain, we'll get a letter R. And we drop the ANE suffix and change it to YL. If we have 1 carbon hanging off of the main chain, we'll call that methyl. 2 carbons, ethyl. 3 carbons, propyl. Notice now an iso prefix on the propyl, still 3 carbons, but now instead of the terminal carbon being attached to the main chain, it is the second carbon, and we start to see this iso prefix, isopropyl. 4 carbons is butyl. Notice here, butyl can be an iso format, secondary, or tertiary butyl. Find the carbon that's attached to the main chain, which is this kind of bond right here. The term iso has 2 branches coming off of that carbon. Secondary is showing that there are 2 carbon branches coming off of the carbon that's attached to the main chain. And a tertiary butyl group would have all 3 carbons coming off of the carbon attached to the main chain. So these are just samples of how we go about naming the alkyl groups, those functional groups that are hanging off of that carbon chain, the longest backbone in that hydrocarbon. So in this chart we're learning the YL group is now given to the functional group hanging off of the longest carbon chain. The longest carbon chain in our structure will always end with ANE, and these branches will have the YL groups. Well, let's take these rules one at a time and discuss them. The IUPAC naming of alkanes, and again, International Union of Pure and Applied Chemistry, that international system that all chemists use to name compounds, both organic and inorganic. First of the rules says the name for an alkane with an unbranched chain of carbons consists of the prefix showing the number of carbon atoms and the ending ANE. We've mentioned those: methane, ethane, propane, and so forth. Number 2 discusses branched chains. For branched chain alkanes, the longest chain of the carbon atoms is the parent chain, and it becomes the root word for naming it. No matter how many twists and turns you use in a compound, find the longest carbon chain, and everything else become a branch off of that chain. Third rule states, name and number each substituent on the parent chain and use a hyphen to connect that number to the name. Let's take a peek at that rule. Here we have 3 carbons in a row. The longest chain, 1, 2, 3. Even if I count it up here, 1, 2, 3, counting backwards, 1, 2, 3, no matter what direction I go, the longest chain I can come up with is 3 carbons. See the root word here? Propane. On that second carbon, we have 1 carbon branch coming off. That gets a prefix methyl. Notice I'm telling you the position with the number. I have a hyphen that attaches it to the prefix meth. And notice here, now for the alkyl group, this YL suffix is telling us it's attached to the main chain as a branch. 2-methylpropane is the name of that compound. Notice no matter what direction we would number those carbons in, we come up with the same name each time. Rule 4 discusses if there's more than one substituent group. If there is one substituent, number the parent chain from the end that gives the substituent group the lowest number possible. So even though this branch is a methyl branch, counting from left to right, this would be called 4-methylpentane. If I counted from right to left, 1, 2, 3, 4, 5, as it's shown on the slide, the number 2 is smaller than the number 4. Therefore, we correctly name it with the lowest number possible. 2-methylpentane. Longest parent chain is 5. Here's the root word pentane. Off of carbon number 2 is another carbon. 1 carbon gets the prefix meth. The suffix -il shows us that it's a branch chain, an alkyl group. 2-methylpentane. If the same substituent occurs more than once, we'll number the parent chain from the end that gives the lowest number to the substituent that's encountered first. We'll indicate the number of times the substituent occurs by a prefix: di, tri, tetra, penta, hexa, so forth. We're going to use a comma to separate the numbers, separate the position numbers, and then again, remember the hyphen to attach the numbers to the words. Here we have a molecule. Let's count. We have 1, 2, 3, 4, 5, 6 carbons in the longest chain, and it wouldn't matter if I went up, I'd still come up with 6 carbons. So my root word, hexane, 6-carbon main chain. I encounter 2 methyl alkyl groups, branches coming off that main chain. They are the same branch, so we're going to use the prefix di to tell us that there's 2. Now notice that the way I numbered, I encountered at carbon number 3 and at carbon number 5, the way I numbered gave them 3,5-dimethylhexane. However, if we numbered going the opposite direction from right to left, 1, 2, 3, 4, 5, 6, now I've reduced them to a smaller ratio. I've got 2,4-dimethylhexane, and that is indeed correct. We have to give it the lowest possible number. So a comma to separate the 2 numbers. The hyphen attaches it to the main name. Prefix di tells us that there's 2 methyl groups at position 2 and 4. 2,4-dimethylhexane. If there are 2 or more different substituents, we list them in alphabetical order. Alphabetical order. So think about what I just said. Methyl, ethyl, propyl, and so forth. These are what we're referring to as alphabetical order. Ethyl would get named first before methyl. Methyl would get named first before propyl. Butyl would get top priority because it starts with a B. So we're naming these alkyl branched carbons in alphabetical order. We number the chain from the end that gives the lower number to the substituent encountered first, regardless of the alphabet. If there are different substituents at equivalent positions on opposite ends of the parent chain, now the alphabet plays a role. The lower number is given to alphabetical order. Let's make a note of that. In this slide, we have an example. I see at carbon 1, 2, 3, 4, 5, 6, 7. No matter which way I count, here's 1, 2, 3, 4. Nope, that's not long. 1, 2, 3, 4, 5, 6, 7. Okay, that is the same structure had I gone straight chain. So the longest possible way I can find the chain is 7. Not because they're written in a row. I sometimes have to play with the find and finding the lowest, the longest chain, giving me the lowest number for my first substituent group. If I had numbered this 1, 2, 3, 4, 5, 6, 7, we actually come up with the same name had we numbered this carbon number 1, 2, 3. So therefore, it really doesn't matter which carbon we call number 1. We're going to have a branch chain, an ethyl group coming off of carbon number 3. What else do we have? At carbon number 5, we have a branch chain. Get rid of those to clarify. There we go. So at carbon 5 and at carbon 3, at carbon 3 is an ethyl. See that? There's 2 carbons there, so that prefix is ethyl. And at carbon 5, we have a methyl. Well, if we had numbered this 1, 2, 3, 4, 5, 6, 7, at carbon 3, we would have had methyl. And at carbon 5, we would have had ethyl. This is saying if we have substituent groups at equivalent positions, so starting from left to right, I get a substituent group, a branch coming off of carbon 3. If I had started numbering right to left, I get a branch off of carbon 3. How do I know which way to begin numbering? That's when the alphabet plays a role. Start by numbering to give the highest alphabetical preference to the E over the M. 3 ethyl, 5 methyl, and then 7 is heptane. Give the lowest number to the alphabetical order. Now, if indeed they were both the same group, it wouldn't matter which way we started numbering. If this had another branch on it, let's just say it did, it would be 3,5-diethyl heptane, and therefore we could have numbered either direction. Alrighty. Number 7. Do not include the prefixes di, tri, tetra, and so forth in the hyphenated prefixes, secondary or tertiary, in the alphabetizing. Don't give them priority. Look at the branch chain root word. So let's take a peek at this structure and try to find the longest backbone. We have here carbon 1, 2, and I'd be terminal if I went to 3, so that's not the longest chain. 1, 2, 3, 4, 5, 6. Not because it's in a row. I could have went up here as well, 5, 6, and I still end up with the same structure, so that doesn't matter. But at carbon number 4, I have a ethyl group. And at carbon number 2, now keep in mind these are 2 carbons up here, I have a dimethyl group. 2 methyls hanging off of carbon 2. Now how did I know to start numbering left to right? Remember, if I can get a number, let me say this clearly, the first substituent I encounter is top priority. Counting left to right, I encounter a substituent group at carbon number 2. If I'd counted 1, 2, 3, the first substituent I encounter is at the 3rd carbon position. Well, position 2 is indeed a lower number than position 3, so I must start counting from left to right. I must get a number that's lowest in the first encountered substituent group. Now at carbon 2, I have 2 methyls. That's dimethyl. But notice I'm ignoring that little D there. Don't use D when alphabetizing. I'm using M, methyl. So alphabetically, ethyl is given more priority than methyl, ignoring the prefixes. So at carbon 4, we have an ethyl group. Notice this, we have a dash, 4-ethyl, dash, 2, 2, dash, dimethylhexane. I'll repeat that. The numbers, then a dash, then the word. then a dash, but the numbers are separated by commas. Numbers to words receive dashes, commas between the numbers, and the prefixes are going to attach directly to the root word at the end. 4-ethyl 2,2-dimethyl-hexane. We made mention earlier that some of these have common names from an older system. The number of carbon atoms determines the name, and the first three alkanes, methane, ethane, and propane. Then we have butane, pentane. Sometimes we start seeing some of these common prefixes, not really IUPAC, but it's worth noting because you're going to see them and encounter them along in common organic books. Let's just take a word, ISO, for instance, is a common thing. Not an IUPAC name, but just a common name. If I see ISO, what that's telling me is on a carbon, I have a branched chain of one carbon going off in each direction. Isobutane, notice it's 1, 2, 3, 4 carbons including the branch, including all number of carbons, isobutane. Notice here there's 5 carbons, 1, 2, 3, 4, 5, including the branch, isopentane. So that term iso is letting us know that that terminal carbon is coming off as a branch. Isohexane, 1, 2, 3, 4, 5, and then here would be the 6th carbon. Iso, giving us this kind of a V shape here at the end. Isohexane, 1, 2, 3, 4, 5, 6, 7. And then if I put another here, here's isooctane. We could get the idea of iso. But interestingly, if I just take a look at, let's say, isobutane, redraw that. Isobutane. Well, what would its IUPAC name be? Longest carbon chain is 3, so I know the root word is propane. Off of carbon number 2 is a methyl group. The IUPAC name for this compound is 2-methylpropane. Its common name, isobutane. That prefix, isobutane, that prefix is letting us know that there's a branch at the terminal carbon there. Let's take a look at isopentane. 1, 2, 3, 4, 5, 6. Whoops, I didn't draw isopentane. Here is isohexane. We'll just use this as an example. Isohexane, there's 6 carbons. Although the longest carbon chain is 5, the term iso is letting us know that the 6 carbons that are in the structure is showing a branch at the very end. Iso is telling us that there are 2 carbons coming off in the branch chain here. But what would its IUPAC name be? Well, going this direction, 1, 2, 3, 4, 5, so I get the number on the lowest carbon to represent 2-methylpentane. Its IUPAC name. 2-methylpentane is the same as isohexane. To come back to this particular structure, 1, 2, 3, 4, this is 2-methylbutane, its IUPAC name. So these common names, one of the examples you hear quite often for a common name is this term iso. It shows that at one end, an otherwise unbranched chain terminates in a branch. The CH3 taken twice is the term iso. CH3 taken twice on the very terminal carbon. That's the term iso. Not IUPAC, but common. Let's take a look at an example now and just kind of pulling a possible example from a text. Number 4, example 4, this is on page 331. We're to write molecular formulas and IUPAC names for each of the following alkanes. I see one, and I'm just going to kind of draw the sketch I see. I have 1, 2, 3, 4 coming off, 1, 2, 3, and 4. So this is the letter A found on page 331. What is its IUPAC and what is its molecular formula? Let's try to find the longest carbon chain. 1, 2, 3, 4. And if I counted 1, 2, 3, 4, I still come up with the same longest carbon chain. So I'm getting a root word here of butane. I notice at carbon 2, I have an alkyl group, a branch coming off, and that has just one carbon. At carbon 2, I have a methyl. We have 2-methyl butane. How many total carbons do you count? 1, 2, 3, 4, 5. And do you remember my trick? 2n plus 2. 2 times 5 is 10, plus 2 more. There's 12 hydrogens in that structure. C5H12 is its molecular formula. Its IUPAC name of 2-methylbutane. I do notice that there's a branch, CH3 on carbon 2. What might be another possible name? That prefix iso that we just talked about. Isopentane would be the common name for this structure as well. We weren't asked that, but it's just good to know. Let me try to draw for us a structure from the letter B in our example. 1, 2, 3, 4, 5, 6, 7. So I'm going to go 1, 2, 3, 4, 5, 6, 7. Kind of putting that there. I have a branch coming down here, one coming off like this. So I've just redrawn the structure as I see it in our text. What is the IUPAC name and the molecular formula for our compound? Well, let's find that longest chain. If I start over here, I come up with 1, 2, 3, 4, 5, 6. How about starting over here? 1, 2, 3, 4, 5, 6, 7. That's longest. Even if I started here, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. The longest way I can come up with is counting 1, 2, 3, 4, 5, 6, 7. So my root word here will be heptane. Now what do we notice? We have a group coming off at 4, and we have a group coming off at 2. The group coming off at group 2 is a methyl, and the group coming off here has 1, 2, 3 carbons in it, and they're a branch at the end. What do we call that? Having a branch with 3 carbons. You got it. Isopropyl. Isopropyl alcohol is rubbing alcohol. You might be familiar with that. This term iso is commonly used in when we put in names for branched chains, the alkyl groups. You'll hear iso quite commonly. So we're going to go ahead and call this iso. Now think of the alphabet. This I does get alphabetized because it's not a prefix. It's not di, tri, tetra. It's part of the name of this group, isopropyl. So being part of the name makes it part of the alphabetizing. So at carbon 2, we have a methyl. At carbon 4, we have isopropyl heptane. Now I didn't fit in that well, but that's the name of it. 2-methyl 4-isopropyl heptane. What's wrong with that? That's not alphabetized correctly, is it? So this would get marked wrong, as I just kind of gave that order of priority to the number, but here's what it correctly is. 4-isopropyl 2-methyl heptane. And I'm glad someone caught that in my reading just now, because it shows me that we're understanding. I knew that I was wrong because alphabetizing gives priority. So 4-isopropyl 2-methyl heptane is our correct answer. Shall we keep trying? Never hurts to keep trying. Problem 11.4 from page 331. Let me get the structure drawn. 1, 2, 3, 4, 5, 6, 7. All right, so 1, 2, 3, 4, 5, 6, 7. That's my beginning part. I have a branch coming up here. I have a branch here, 1, 2, 3, and another branch here. So redrawing that structure. Let's work to find the longest carbon chain. Okay, so let's just kind of pick, thinking that this journey might be the longest chain here. 1, 2, 3, 4, 5, 6, 7, 8. I get up with 8 carbons in that direction. Let's keep trying. What if I started here? 1, 2, 3, 4, 5, 6, 4, 5, 6, 7. Yeah, it looks like the longest way I can find this is indeed our original guess there with the 8 carbons. So longest carbon chain looks like an 8, and we now have the root word octane. Now let's begin thinking about numbering correctly. I notice that the way I have it numbered here, number 7 gives me my first branch, so I can see that that's going to need to be fixed. So I'm going to have to renumber those correctly to give priority to the lowest branch. So I have 1, 2, 3, 4, 5, 6, 7, 8. That gives me at carbon number 2 a methyl group. So let me just jot down what we have. 2-methyl. I have another branch at carbon 5, and that looks like an isopropyl. Notice how I'm using iso. It's a branch with 3 carbons. 1, 2, 3. The branch with 3 carbons is isopropyl. Think about alphabetizing. Iso gets preference over methyl. 5, isopropyl, 2-methyl, octane. Shall we try another? And this will be the last example. Let me get this structure drawn. 1, 2, 3, 4, 5, 6, 7. Start up. 1, 2, 3, 4, 5, 6, 7. Just trying to model what I have in my book here. At this point, I have a structure like this, and then an iso coming down here. All right, looks like a bunch of squiggles. We're trying to name that compound. IUPAC names. We go to work trying to find the longest chain. That's always the first step. Where can I find the longest chain? I'm going to kind of consider what I've got going on here. 1, 2, 3, 4, 5, and it wouldn't matter. 6, 7, 8. I can find one going there. 8. 1, 2, 3, 4, 5, 6. Nope. 1, 2, 3, 4, 5, 6, 7. Nope. 1, 2, 3, 4, 5, 6, 7, 8. And that indeed is the same as we numbered them there. So it looks like, again, I can find the longest chain, so giving me my root word octane. I started up here 1, 2, 3, 4, 5. However, if I renumber 1, 2, 3, 4, that's a lower number for that position on the substituents. So at carbon 4, what do we have? Well, we have 1, 2, 3. We have a propyl group. And that's a straight chain, isn't it? So it's just 1, 2, 3, 3 carbons in a straight chain, so propyl. But also we have this isopropyl group here at carbon 4. Again, 3 carbons, but in a branch format, so that is isopropyl. So when I name this, iso gets preference because of alphabetizing. 4, isopropyl. 4, propyl, octane. The other part of this we have to kind of back up and consider is the other part of the question I left off. It asked you for the molecular formula. How many total carbons do you count in this structure? I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 total carbons. 2n plus 2, so 2 times 14 is 28. 2930 is its molecular formula. Back up with me on your paper and try that with this example. How many total carbons did you count? I'll keep it blue. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. C12, 2 times 12 is 24. Add 2 more. C12H26, the molecular formula. And I left off this guy here as well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. C11, H22, 23, 24. I highly recommend spending some time with some example problems even in the back of our chapter. Keep practicing naming IUPAC for the alkanes, and when you feel confident, start up with the next lesson.